Hi, everyone. So I'm Issa. I think the most important thing I have to say today is that it's Thanksgiving over here in the States. And so my kids are over there. There's just a very thin door separating us. And so if there is a massive eruption of screaming, it's not someone dying, it's my daughters. Okay. What I want to talk about today is some phenomena that happen when you have a randomized trial and you try to analyze it together with an observational study that tries to emulate the trial as closely as possible. And I'll describe the terms in more detail as we go on, but I want to talk about benchmarking and joint analysis using these two data sources. Okay, and so this is still work in progress, and so comments are very welcome. It's easy to find my email, and I'm happy to hear your thoughts and ideas about this. And it's also joint work with a number of people, including Anthony. And then I also like to say my talk is going to be very algebraic, very analytical. It's possible to do everything we will try to do together with graphs, with causal graphs, but there's just not enough time to do this in one talk. And so I have a link here for a paper where we sketch some of these ideas. So if you like graphs, it's going to be disappointing. Okay, so I want to talk about comparing randomized trials and their emulations. And one reason to talk about this is because everyone seems to be doing this. The FDA is interested in it. There's a massive Sentinel-sponsored program going on in the States. The insurance companies that have a lot of routinely collected data are interested in doing that. And I know there's many people in your group interested in this. And it's been going on since forever. And sometimes people will attempt to do it just by using published information, or sometimes they'll do it by using actual handcrafted observational analysis. And then they'll compare with some kind of trial that they thought was similar enough. And these comparisons, I think, are always interesting. They are guaranteed to be controversial. And I have found them quite hard to interpret. And so I'll introduce some terminology for those comparisons, and our goal will be to somehow formalize them so that we can understand them a little more deeply. So I'm going to use the term benchmarking for a comparison that's done to learn whether the observational methods can produce causal estimates. And so it's a comparison of the trial and the emulation, aiming to evaluate the methods used in the emulation. And the term joint analysis or joint inference for some kind of effort that combines the data sets so as to learn about causal effects using treatment and outcome information from both. Okay, now let me introduce some notation so that we can be concrete. I'm going to use X for covariates. I'm going to use S for the source study. So S equals 0 will mean the observational emulation of the trial, and S equal 1 will mean the trial itself. And I'm going to use A for treatment. I'll just conventionally say A0 is the control group and A1 is the treated group, but these labels don't really mean anything. There's just two treatment groups. And I should say it's possible to have many more. You could consider multi-valued treatments. It's just not as profitable to have the notation for many more. No conceptual ideas are different from the multi-valued case to the binary case. And then I'm going to use a binary outcome, which again is not required, but it just makes everything very transparent when we try to do calculations. And so I'm going to say outcome Y equal 1 means dead and 0 means alive. Okay, and you can already tell this is a very simple setup. it pays to work in the simple setup to build intuition. And then if you have questions about how this can be broadened to much more realistic cases where maybe the treatment is time varying or the outcome is longitudinally collected, I'm happy to talk about that. But I feel the essence of the problem can be done in this simplest case. Okay, and so this setup is so simple. You can really summarize all the data in a table. And so we don't need to memorize the numbers or anything like that, but I think it helps to have a structure in mind. And so what I'm thinking about is there is a source study up here, and that's the S1, so that's the trial. And so all this block up here is the trial. And then the 0 is the emulation. It's the observational study that tries to be as close as possible to the trial. And so that's the bottom half of the table. And then within its study, we collect covariates. And again, I'm going to use just a binary one to make everything very simple. And so the X covariate is either 1 or 0, and that's available in the trial and the observational study. And then within levels of the covariate and within each study, we have the treatment varying either 1 or 0. And then there's people, and these people experience outcomes, and that's what's collected in the last two columns, the outcome status of different people by study, covariate level, and treatment group. Okay, again, we don't need to remember the numbers, but I made them big so that we don't have to worry. And this is a completely artificial data set. It's big enough that we don't need to worry too much about sampling variability. I'll make some allusions to statistical analysis, but I don't plan to go too deeply into that. If you're interested, I'm happy to go deeper in the question session. Okay. Now, we want to do causality, so I'll have to introduce some more notation. This is my last piece to talk about counterfactual outcomes. So these are outcomes under intervention to set treatment to a particular level, possibly contrary to fact. And so for every individual, I'm going to think of this Y superscript little a. And for little a 0 or 1, I get two of those potential outcomes. I get the Y superscript 1 and Y superscript 0. And these mean what would happen to the same individual were they treated, little a equal 1, or were they to be untreated. So that's little a equals 0. And so I'm going to think in the usual epidemiologic way that these potential outcomes are well defined for every individual, regardless of the actual treatment they received. Okay. And so using those outcomes now as random variables, I can define things like the probability of the outcome under different interventions. And since I'm thinking of two populations, the trial one and the observational emulation, the S1 and the S0, I may think of these conditional potential outcome probabilities where the conditioning is on S. So it's the trial or the emulation. And so you can think of these as counterfactual risks since our outcome is binary. Okay, causal effects are going to be contrasts of the probabilities for different A and little s values. And for example, the causal risk difference in the population underlying the emulation is going to look like this. It's the probability that Y superscript 1, that's the outcome under intervention to set treatment to 1, is 1 among the S0s minus the probability that Y superscript 0 equal 1 among the same group. I'm always going to be considering contrasts where the S is the same, either the S0 or the S1, since I'm not thinking of intervening on the trial explicitly here. Okay, and so this is what everyone is taught to call the causal risk difference in the observational study. It's just that I've made the observational study explicit by writing S equals 0 in the notation. Okay, and so we're going to play a number of games. Okay, the games are, we'll have the causal estimate, it will have these risks and their differences, and we have to write it in a way that uses only the observed data, the data in the table. And if you remember, if I go back, you'll see this table doesn't have counterfactuals on it. So we need to rewrite everything such that it doesn't involve the counterfactuals. And so what I'm going to be doing is I'm going to be stating assumptions. These assumptions will allow us to write the causal estimates as functions of the observed data. And that's good. We want to do this because once we write everything in terms of the observed data, we know that in a simple problem like this one, where everything is a 2x2 table, I can have hopes of estimating all the quantities. And so if I can write the causal things I want as functions of the observed data which I have, then I can use the data to do estimation and to do statistics. And what's the pain and joy of causal inference is that the critical assumptions are always going to be untestable, with perhaps one little exception. Okay, and so since the assumptions are untestable, sometimes we can make progress by using study design. And so, for example, in the randomized trial, the study design ensures that certain assumptions hold, but sometimes we do observational epi. That's what happens on the emulation side, on the observational study side, and life is just hard over there. You just have to live with it. The fact that you have to assume things that you can never know for sure are correct. Okay, and so again, in the spirit of making everything simple and being able to make progress by focusing on the important conceptual ideas, I'm going to state 3 assumptions here and never revisit them. Each of these deserves separate consideration. In any applied work, you definitely need to spend time on these 3, but we don't have, we have less than an hour, we have 3/4 of an hour, and so we just can't do it. If these are of interest, I'm happy to talk about them more. So the first one is some kind of positivity assumption, where I'm going to assume that for every level of the covariates, the probability of being in a particular study, be it the trial or the emulation, and receiving a particular level of treatment, A1 or A0, is positive. And so I'm not claiming that this is guaranteed by design, since that would not be true for the S0 parts of this conditional probability. All I want to do is just put it aside, agree to work with me on this, and then if you doubt it, we can revisit it. The second assumption is perhaps an even bigger ask of you to trust me and work with me. This one says, for a person, be they in the observational study or the randomized trial, who gets treatment big A equal to little a, their observed outcome has to equal their potential outcome. And so sometimes this is called consistency or consistency of potential outcomes. I claim that it's a rather strong assumption in the benchmarking case. But again, with the principle of work with me here, let's leave it aside for now. And then, we already said this, everything is going to be discrete. You saw that beautiful table, all the cells had numbers in them. And so since everything is discrete and has very few levels, everything is really binary, I'm not going to be using any models, and I'm going to assume the sample size is big enough that I don't need to worry about sampling variability. And if sampling variability worries you, just take the numbers on the table we had and multiply them by 1 million. Okay, you'll get the same answers that I get, and then at that point, I think you would never worry about statistics. The reason I do this is because it's not productive to think about statistics and causality at the same time. And so we'll do causality first, and if you care about the statistics, I'm happy to address it later. Okay. So as I said, we're going to play a game. The game will have multiple rounds, levels, and so this is the practice round. Okay. So when you tell people I just ran a trial and it was just a 1-to-1 randomized trial, which is how I generated the data here, people will say, oh, I know. Because you did a trial, there is no confounding. You don't even need to adjust for covariates. And the way to express that idea is to say that the counterfactual probability of the outcome under treatment little a in the trial, that's the S1 here. Do you see if I highlight things? Anthony, can you give? Okay, great. So this is like the potential probability, the probability of the potential outcome under treatment little a in the trial, but that's for everyone in the trial. And so that is equal to the probability of the potential outcome under treatment little a being 1, so that's the same. In the trial, that's also the same among those who are assigned to treatment little a. So this essentially says the arm that gets treatment assigned to treatment little a is exchangeable with the entire population in the trial, which makes sense by randomization. Okay, so when I have this, what I can do is I just wrote the assumption. So this first row is exactly copied from above, is the assumption. And then I can use consistency, which, remember, consistency said if big A equals little a, then the Y superscript little a equals the observed outcome. And so I can just replace the counterfactual outcome with the observed outcome because I'm conditioning among the people who get treatment big A equal little a by consistency. And so that's fantastic. That's why this is a practice round. It's super quick because we rewrote what we wanted, what we were interested in the trial, which was a potential outcome probability. We wrote it as a function of the observable variables, because you can see here the counterfactuals have disappeared. And so this means I can just go in the data and do calculations. But before we do this, just to say the causal risk difference is just the difference between the potential outcome under treatment Y, treatment little a equal 1, and the treatment little a equals 0. And so I just take the difference of these two expressions by plugging in little a equal 1 and 0, and I just get the marginal crude risk difference in the trial. And so I know now no one needed this to happen. This slide is kind of review. It just pays to have it because then we get in the mood of using the consistency assumptions and we understand the game. Okay, and so now we can go on and do calculations. I can just estimate, if you will, each of these quantities from the table. Now my arithmetic is terrible. I would never trust me, but I use the computer. And so I think if you go and check, you'll get the same answers as me. So I just divided the number of people with the outcome in the trial under treatment A1 by the total number of people assigned to treatment A1 in the trial. I did the same for the people who got the outcome in the trial among those who were not randomized. That's the second term here. I take the difference and I get something like 13.8%. Okay, so the treatment increases. It's a dangerous treatment in this example. Okay, since the outcome was death, it increases it by a substantial amount. It's completely artificial, so the numbers are bigger than what you would expect in any real clinical trial. But again, it helps to have big numbers so that we can see without getting lost in the decimal digits. Okay, so that's a 13.8% crude risk difference in the trial. Okay, so now this is level 1, it's easy. I'm going to make another assumption, which is also very reasonable in the trial, and then we'll see how the results change. And I know it gets boring with the calculations, but I want to reach a conceptual piece that requires notation. And so you have to bear with me for a little bit, and then we'll get fireworks, okay? Okay, so here I'm making the exchangeability assumption, the assumption of no confounding over treatment in the trial, but I'm making it given covariates. I'm conditioning on that nice covariate that I had in the table. Otherwise, nothing changed. So I condition on X, I'm working in the trial, and then I'm saying the probability of the counterfactual outcome given covariates in the trial is equal to the probability of the counterfactual outcome given covariates in the trial and given treatment. And so this again means that within levels of the covariates, the treated groups are exchangeable with the overall population. Again, a reasonable assumption because I just flipped a coin to assign people. And so if it holds marginal, it will also hold conditionally in this case. Okay, now the calculations here get a little more complicated but not too much. And again, we're going to build off this to do the trial, to do the observational emulation. So it helps to do every case step by step so we can see where the differences are. Okay, so this is the marginal probability of the potential outcome, still only working in the trial. I'm just offering you, if you will, a covariate adjusted analysis of the trial. And then what I do is I write the marginal probability of the potential outcome in the trial as a marginalized conditional probability, where I take the conditional potential outcome probability always in the trial, and it's now conditional on x equal little x, and I average it over the distribution of the covariates in the trial. And so the notation here may be a little scary with that big sum, I know, but if you think about it, what's happening is I just estimated the risk in its level of the covariates. I just wrote the potential outcome risk, forgive me, the potential outcome risk for its level of the covariates, and then I averaged those conditional potential outcome probabilities over the distribution of the covariates, which makes sense. You have to weigh them by the number of people in each covariate level. And then the next step just uses the exchangeability assumption. So I just add the a equal little a conditioning. And then as always, my last step is going to be consistency. So if a equal little a, then superscript little a is equal to the observed outcome. And so now we have something that everyone who's done any kind of standardization in real data should be familiar with. I'm taking the observed now risk of the outcome among covariate level equal little x in the trial and among those treated with little a, and I'm averaging it over the entire group of people with x equal little x in the trial. It's very important to notice that everything is in the trial still, all the terms and conditioning on s equal 1. And so really all I did is I did an adjusted, if you will, analysis, because I'm conditioning on the covariates and then I'm averaging it over everyone in the trial. And we've achieved our aim, this level, we terminated this level because this quantity, this entire sum depends completely on observable variables. There's no counterfactuals. So again, I can go to the data and do calculations. The risk difference is always a difference of two of these for a equal 1 and 0. So, that's not anything new. That's the risk difference. It's the difference of two observed data quantities. So now I can go to the data and do calculations, right? And the calculations now are a little more involved. And so I definitely had to use the computer, but full transparency, what's happening is the computer is saying y1 among x1 and a1 divide by the total number of people with x1 and a1. That's how you get this term. You do the same for the a0, so that happens down here. You do the same for, forgive me. Okay, you do the same for the x0 level, and then you average them over the distribution of the x. Excuse me. And again, notice my data analysis parallels the identification result we have up here. I told you to pay attention that everything is given as 1. And you can see the only table my computer needs to see is the part of the table that has s equal 1, right? The bottom part s equals 0, I have just removed. And so I get a risk difference of 13.8%. And so that's essentially the same. They differ in the 4th or 5th decimal. And why are they the same? Well, my trial was very big. This adjusted and the unadjusted analysis we saw target the same causal quantity. And so it's no surprise that we would get a very similar number. Now, if we were doing statistics, this result, the result that conditions on x and marginalizes over the distribution of x, will tend to be more precise. This is what the people who are trying to advocate for covariate adjusted analysis in randomized trials are talking about. You can improve efficiency while estimating the same quantity and without making unnecessary assumptions. Again, we won't concern ourselves too much with estimation today, unless if you have questions. I just thought it's important to know the reason you would go through the trouble of adjusting for covariates in the trial is primarily to improve efficiency. Okay. So again, I feel like up to now I've been doing mostly review, and to be honest, this next step is also largely review in a group where I know many sophisticated observational analyses are being done. But again, bear with me, we're building up to the fireworks. Okay, so now I'm going to do the emulation. We want to analyze the observational data, and so that's level 2 of the game. Now, in our hearts, we know that if there is confounding in the observational study, you should not use an unadjusted, you should not use a crude comparison. So what I did is, just for illustration, I performed the calculation. So I took the observed outcome probability among the treated and the untreated, but notice now I'm working in the emulation, in the observational study. I take the difference, I get 0.2. Now this is quite different from what we found in our trial analysis, which was 0.13, 0.8. And so when we see that it's not the same, we say, okay, maybe that's fine because I know there is confounding, right? The crude won't equal the unadjusted. So I have hopes of improving my observational analysis. Maybe it will agree more with the trial, and so on. And again, these differences are highly statistically significant because we're working with a huge data set. Again, you don't need to worry about statistical inference. Just saying this difference of 0.6, 0.2 is pretty huge in this setting. Okay, so now we have to make a critical scientific assumption. It's one that is in general not given to us by design. And so that's some kind of no confounding given the covariates in the observational study. And so what it says is, given the covariates, so you can see I'm conditioning on X everywhere, in the observational study, the probability of the potential outcome within levels of the covariates, again, is within levels of the covariates is independent of the treatment received. Okay, so that's what allows me to put the A equal little a in the conditioning statement. And so again, this means that the people in the observational study within levels of the covariates who get treatment little a are exchangeable with everyone with that level of the covariates. So this one is a big assumption. Everyone knows to worry about it. And that's why in real analysis, in practical work, we would try to collect lots of different variables in X. X would include a lot of information about every individual so that we can hope that within levels of this high dimensional X, the assumption holds. I agree, in any reasonable analysis, we would never use just a binary confounder. This is just like saying my only confounder is going to be, let's say, whether you have insurance or whether you had high blood pressure at baseline. That's not a very serious analysis in the real world, but in this simulated example, the univariate binary X that I created is sufficient for this assumption to hold. Okay. And then what happens is, once we make that assumption, we can use what we wrote before to make progress, to write the potential outcome mean. That's the same because it's y is binary. So the probability of the potential outcome in the observational study, right? Notice again, now we have S0. We want to write it in terms of observable variables. And so what happens is, I have to use the law of total expectation in the first row. So all this is saying is, if you average the conditional potential outcomes over the distribution of the covariates, you'll get the marginal potential outcomes. So that's reasonable. It's just mathematics, no assumption. I mean, the only assumption that would be needed is some assumption about y, but y is binary, and so it meets that assumption. It's like very essential probability properties that we're using here. Then we use the important scientific assumption. That's what allows us to bring in A equal little a. And so we replaced the conditional potential outcome probability given x equal x in S0 with the conditional probability given x equal little x, s equals 0, and a equal a. We brought in the treatment. And then the last step uses consistency. When a equals little a, y superscript little a equals observed y. And again, we're done with this level of the game, because this bottom sum, intimidating as it may appear, is just an averaging of the conditional probabilities that we can get by looking among x equal little x, S0 in treatment little a, and then averaging over the distribution of x in S0. And so, similar to before, if I take the difference of two of these terms for little a1 and little a0, I get the causal risk difference in the observational study written as a function of the observed data. And for people in the know, this is sometimes called the Z formula for non-time varying or for point treatments. And it is a special case of what you would get if you applied the Z computation algorithm. But for us practical people, all we have to do is we have to estimate these probabilities for different x levels, estimate these probabilities for different x levels, sum over the different x levels, and then take the difference to compare. And so I did this here. And unfortunately, and notice I'm only using the S0 data. I never have to touch the S1 data because everything here only involves conditioning on S0. So I'm just analyzing the observational analysis like you would do when you have a big complex observational study where the x's are high dimensional. And then I use this part of the data. I won't bother you with the numerical calculations, but the risk difference that you get from this data, if you apply that formula, is even bigger. So now we have 0.227, 22.7%, which is, if you recall, bigger than 20%, the 0.2 that we got in the crude analysis of the observational study. And it's way bigger than the risk difference we were estimating in the trial, which was 13.8% approximately, 0.138. And so that's terrible. That's terrible. Our result in the observational study is different both from the crude analysis and from the trial. And so many times people will do these informal calculations, informal comparisons, informal benchmarking, we may call it, where they say, oh, this adjusted observational analysis returned a substantially different answer from the trial. It must mean that there is residual confounding, right? Of course, that can't be the case here because I made the data. And if you trust me, X was the only confounder. So there has to be something else. And so, you know, if we think about it a little bit, we've eliminated confounding because this was an artificial data set. So, you know, the only explanation that remains is to say maybe, you know, there is effect modification, meaning the treatment effect is different over X, and people have different X distributions in the trial and the observational study. And so they'll say, oh, this happens because people select into participation based on their covariates. When we invite them to be in the trial, people who have a particular X value may be more likely or less likely to agree. And so that would be some form of selective participation. And so what I'm going to do next, and this has been done in applied work only a few times. I think the group from UNC has a couple of papers, and Sarah Lodi, I think, was the first to do something like this in the context of an HIV observational study. But basically, what you can do to make some progress is to say, suppose there was no confounding over participation. That is, suppose given the covariates, the potential outcome probability in the trial given covariates is equal to the potential outcome probability in the emulation, in the observational study, given the covariates. And so this is some kind of independence of the potential outcome from S given the covariates. So that's another critical assumption. It's an assumption that cannot be determined just by looking at the data. And so I will tell you, I created the data under this assumption being correct, but in the real world, you would never know. But once you make that assumption, the calculation is a little more tedious, one more extra step. But what you can do is you can write the potential outcome probability in the observational study, more accurately perhaps in the population underlying the observational study. You can write it as a function of the observed data. It's just that you need to use this assumption, and this is what makes you have to take an extra step. So let me walk you through these steps a little more carefully, because this one, you need to be convinced about it to make progress. So the first step is always some kind of law of total expectation, law of total probability step. And so I'm just marginalizing over the X distribution in the S zeros. But now, because this assumption connects the trial and the observational populations, it allows me to replace this term with the S1 version of it, right? So I'm just using the assumption going from this to this. And now we have this funny expression that is an average of the potential, the conditional potential outcome probability in the randomized trial, but averaged over the distribution of the covariates in the observational study. And then again, since this part comes from the trial, I don't have confounding in the trial, so I can put the A equal little a conditioning here, because given covariates in the trial, the potential outcome is independent of treatment. So I can do this step, and then I can invoke consistency to replace the potential outcome with the observed outcome among the people getting treatment, big A equal little a. And so again, success, we've won the third level. We can write the potential outcome mean, the potential outcome probability in the observational study as a new different function of the observed data. And this function, again, is kind of peculiar and interesting and weird, because it has the probability of the outcome given covariates in the trial among those treated with little a, but it averages it over a different population. It averages it over the population of the observational study. Okay. And so again, I can just take differences of two of these terms for big A equal 1 and big A equal 0 to get the risk difference. And so if this assumption is true, I just have a new way of getting the risk difference in the observational study. Okay, and this is just copied from the previous slide. And again, this is now quite interesting. This term will get the usual way from the randomized trial part of the data, but now I need to bring in information from the observational study. And so I made this little mini table of the X distribution over the S. And if I wanted to torture you, I would ask you to do the calculations, but I did them on the computer because I'm not a horrible person. And it ends up that the risk difference here is also 0.22.6, which is very, very similar to what we found in our adjusted observational analysis, but it's very different from the crude analysis of the observational study, and it's still very different from the trial. And so we have two pieces of evidence. This analysis, which we might call a transportability analysis, since it carried things from the trial to the S0 group. So the transportability analysis and the observational analysis, two pieces of evidence that relied on slightly different assumptions, give us the same conclusion, roughly 22.6, 22.7%. And they disagree a lot with the crude analysis of the observational study, and they still disagree with the analysis of the trial. Both the crude and the adjusted analysis of the trial said 13.8%, right, percent. And so both of them very different. And so now we are in trouble, because we had two analysis that somehow used part of the observational data and they agree, and then we have the trial have a different result, and then people get really upset and they say observational studies rely on assumptions and they should never be trusted, always just do trials. And so perhaps though, since this is an artificial data set and I made it so that all the assumptions were true, perhaps we need to be a little more thoughtful and ascribe the difference to effect modification and selective participation in the trial. Okay, so now, before we reach any conclusions, this is where the fireworks happen. So if you've been tuning out for the review parts, this is the good stuff. Okay, so what I'm going to do is now I'm going to collect all the critical assumptions together and see what was happening when we were doing calculations. So in the observational analysis, we assumed there was no confounding of treatment, and this looked like this expression here. So the YA was independent of treatment given X in the observational study. And then in the transportability analysis, that was the last analysis we went through, we made some assumption that the potential outcome is independent of S given the covariates. And so that's how we wrote that assumption. But since Y and S is binary, it's the same as saying it's extendable with everyone. Okay, so now already your spider sense should be tingling because the left-hand sides of these two assumptions are the same. The right-hand sides are different, but the left-hand sides are the same. So let me work with each of these red terms first. Okay, so what we did in the observational analysis is we said the potential outcome given covariates in the observational analysis is equal to the observed outcome probability given covariates in the observational population, in the population underlying the observational study, given treatment A equal little a. So that's the rewriting we used in our derivations. In the transportability analysis, we said the potential outcome probability given covariates and S equals 0 is equal to the observed probability of the outcome, probability of the observed outcome, given the covariates in the trial among those who got treatment big A equal little a. So we used our assumptions to show this is equal to this, and we used another set of assumptions, the no confounding in the observational study assumptions, to write the same red term as equal to this expression. And so at this point, we should say, wow, this is all the fireworks you can get in causal inference. It doesn't get more, I mean, it's not a visual kind of fireworks, but this is going to be the main result I want to talk about as a concept. And so, I'll just copy the final steps. So this is what we did in the observational study. This is what transportability uses. And so now I always say, when you see two things that are the same on the left-hand side, there should be an unstoppable urge to set the things on the right-hand side equal, which I did here. And so this is an interesting implication because it follows from all the assumptions being true that the probability of the outcome given covariates and treatment in those not in the trial, those in the observational study, is equal to the probability of the outcome given covariates and treatment equal little a among those in the trial, in the population underlying the trial. And so you see the only thing that's different between the two terms is the switch from S1 to S0. And so this means the outcome is independent of S, given the observed outcome is independent of S, given covariates and treatment. And this is an implication that can be evaluated in the data. In simple data like ours, it can be done. It can be done just by taking some kind of tabular analysis, or you could just do a non-parametric regression of Y on X, A, and S, and then evaluate that against a regression that just doesn't have S and see if you get the same probabilities. Any kind of test for conditional independence in 2 by 2 by 2 tables will work here. And so that's quite interesting, because it means, as now becomes obvious from our calculations, that each analysis that we were doing relies on assumptions that are entirely untestable and non-parametric. But when we say all the assumptions have to hold together, then we get an observed data implication. I should say, graphically, this is a fairly easy result, and even algebraically, I went through the steps in painful detail, but it's not a hard result to get. The reason all this is kind of easy is because this case was constructed to be relatively easy. And so now what I want to do is I want to think about the implications in this simple case and see what this means for any kind of complicated real-world emulation and benchmarking and joint analysis you may attempt. Okay, so let's go down that road. So the first thing you need to ask is, will this ever be exactly true? Will I ever have an observational study and a randomized trial where there is no confounding whatsoever in the observational study, and the participants and non-participants in the trial and the observational study are also exchangeable given the covariates I got? So I say, if we are honest, probably not. I feel your group, and this is not pandering, but your group is probably the closest I've seen people come to this, because you have large trials, you have large observational studies, they collect data in a harmonized way within a registry, and you could think of applying the same measurements and having a rich enough set of covariates that the assumptions hold. But even in an ideal setting with very rich, very high quality data, I don't think we would ever believe something like the absolute lack of confounding and absolute exchangeability between trial participants and non-participants in the trial to be true. Now, I need to say, just because I promised to say something about joint analysis in the title, if it were true, it means you can just ignore the source study. You can ignore whether people are in the observational or the randomized part, and you can analyze the observational data and the trial data entirely by pooling it, okay? And you can see this manifests by the S1 or S0 terms completely disappearing here. And so all I'm doing is I'm now taking the probability of the observed outcome, given covariates and treatment, but I'm not conditioning on the trial, or the source study, so trial or emulation. And then I'm averaging over the emulation. I'm averaging over the people not in the trial, because usually we think of those people as more representative of the target population where the treatment will be applied in practice. So this is the holy grail of evidence synthesis, sometimes called cross-design synthesis. And I won't bother you with numbers. In our example, the results agree nearly completely with the observational analysis with adjustment on X and the transportability analysis, and they disagree with the others. They disagree with the analysis of the trial. And sometimes people will say, why do I need to do this joint analysis? Well, if the assumption is held exactly, the joint analysis will just always be more precise than the others, because it uses outcome information from everyone, not just from the trial or just from the observational study. And so this is the slide where I try to summarize conceptually what's been going on. And I feel like this may be the real contribution from this talk. The calculations I showed you, especially if you're technically inclined, are pretty obvious. And most of the parts that I used have been discussed forever. The transportability stuff has been written in many ways by many different groups. The confounding parts is ancient knowledge by this time. We teach it in Causal Inference 101. But putting them together, I think, leads to this table, which has interesting implications. So this table says there are 4 states of the world. Either there is or there is not confounding in the emulation. and either there is or there is not the ability to transport. So either the people in the trial and the people not in the trial are exchangeable given covariates or not. Now, this is not to say that the only assumptions that matter is the confounding and transportability assumptions. Positivity matters, consistency matters, and we had to rely on them very heavily. I'm just saying, if you are okay assuming positivity of the probability of treatment and participation given covariates, and you're willing to assume consistency because your scientific question is such that it makes sense, then the problem boils down to, is there confounding in the observational study? And are the people in the trial, can you transport from the trial to the observational study, which is the same as saying, is the observational study and the trial participants exchangeable given covariates? And so there is 4 possible combinations of these things. And so the best one, the one that we would love to be all the time, is the case where there is no confounding and the trial and the observational study are exchangeable. So no confounding and transportability assumption hold. Then we found out that this has to imply that the outcome is independent of participation given covariates. The emulation result has a causal interpretation, and you can formally compare the estimate of the trial. Actually, I should say the transported estimate from the trial to S0. You can formally compare that against the observational analysis, and you should expect them to agree within sampling variability. Now, that's the good news. This row, the top row, is the good news row. All the other rows are bad in one way or another. What makes, though, the other 3 rows particularly bad is that you cannot use the data to tell in which of these 3 rows you happen to be. So you can, in theory at least, do the statistical test that if it fails, so if the outcome is not independent of study given covariates and treatment, you know you're going to be in the bottom 3 rows. I'm going to leave aside all the complications and caveats with testing, but in the simple example we worked, testing is a possibility. So you test, you reject, you know you're in the bottom 3 rows. Well, if you're in the bottom 3 rows, life is very hard because you can't tell the bottom 3 rows apart using the data. All you know is you're not in the first one. And even that will be tenuous in real world applications where X is high dimensional and statistical testing is challenging, and maybe there is power issues as you would expect. Now, in the bottom 3 rows, if you have confounding and transportability holds, and you somehow knew you were in that row, you could benchmark. So you could obtain an estimate in the observational study. That estimate does not have a causal interpretation. And then you will find that your non-causal observational study result is different from the transportability analysis of the trial to the observational study. And so that's why benchmarking is possible, but you'll find a disagreement. The other 2 cases are also bad. So if there is no confounding, but you cannot transport, then your emulation has a causal interpretation. Your observational study has meaning because there was no confounding, but its result is going to be different from the trial, and it's going to be different from the transported trial estimate to the observational study. And so benchmarking is not very meaningful because you're comparing a result that has a causal interpretation, that's the observational study, against a transportability analysis that has no causal interpretation, since the populations are not exchangeable. And then the bottom row, I think, is the one we know and love from conventional epi. If there is confounding in the emulation, then you do not have a causal interpretation of your observational analysis, and you also do not have a reasonable transportability analysis, so you can't really compare. And so to conclude, I use the formal framework in the simplest possible case, and I try to do the calculations which were tedious and not too hard, but I tried to do them very transparently so that you could see where things were happening. And so we have a framework for benchmarking and even joint analysis if you're lucky. But I think the value of this discussion is mostly in the table we saw at the end. It's mostly in the heuristics for thinking when you see disagreements. And the point of those heuristics is you have to combine your assumptions. You have to combine them with very sophisticated in real world data, not in this case, but in real world analysis, very sophisticated statistical analysis. And even then, in the end, your conclusions will largely be qualitative and judgmental, because even though you're doing extensive statistical analysis, the real hard work is in thinking which analyses are plausible given your research question and data and underlying populations, and triangulating different analyses as we did here in the simplest case. And with this, I'll stop. I know I'm a little longer than I